Okay, what about something like that? Let's take a look at this. So if we want to do a table, do a sketch for a rational function. What's the stuff you, without doing any calculus here, what's the stuff you can tell me about this one? What you say, Katie?
Well, I was just gonna say factor the bottom.
Good, factor the bottom, factor the bottom. So if we factor the bottom, what do we get? So x minus 6, x plus 5, okay. So that's good. That tells us, now, how's that useful? No, we don't need to do that.
That's what
Those words undefined.
Okay, so it's undefined at 6 and negative 5, and what's going on at those places? Everybody agree? Right? Because there's zeros at the bottom but not the top. So already, without doing any calculus, we can start to add some stuff to our table that's important. So we know the domain is all real numbers except for those places, right? Okay, so for negative infinity and positive infinity, we get at negative 5 and positive 6, we get places where the function is undefined. And the reason it's undefined is because the bottom is 0 and the top is not. So we can right away just call those vertical asymptotes. And those are going to split our function. Look how you can already see that's going to split our function vertically into different regions, right? Okay, good. What else? What else? How about limits? Can we do anything with limits here? This takes us back a long ways.
X approaches to y versus
So if we have a rational function, right? If we have a function, now think back to, this was like a long time ago. The limit of a rational function where the bottom is a bigger order polynomial than the top as we approach positive or negative infinity. What are our rules for rational functions? Let's just remember those real quick.
approaches 0.
'Cause this is stuff, this is good review. So if we have R of x equals P of x over Q of x, where P of x and Q of x are polynomials. That's the definition of a rational function, right? So if we have rational functions, what happens in the case where the leading coefficient of the top is bigger than the leading coefficient of the bottom? Okay. Then the limit of our function as x approaches plus or minus infinity is given to us, what is it?
0.
The top is higher.
Oh, the top is
What did we say about that? Remember? Like an example would be if we took the limit of 3x cubed minus x plus 1 over 2x squared plus x plus 4. What do we say about that?
approaches.
Yeah, we said there's no limit, right? Remember that? We said there's no limit, and we had to just look to see what the end behavior of each end was, but there are no asymptotes there, right? So there's no asymptotes. Now, what if we get same word? Top and bottom. So for example, the limit of 3x squared minus 1 over 2x squared plus x plus 4. Limit as we approach plus or minus infinity. What do we say about that?
approach that we have.
3/2, right? Then we take the ratio of the leading coefficients. Okay, so we do get a horizontal asymptote, and it's at y equals ratio of leading coefficients. So in this case, the limit is 3/2, right? And then the third case, what if bottom is higher order than top? Limit of 2x squared plus x plus 4 over 3x cubed minus 1.
0.
Remember that? So then we said the bottom is going to go to infinity faster than the top does, and so you just get 0, right? Y equals 0 is our asymptote. Okay, so which one is it?
Third, higher order than top.
Higher order on the bottom, so if we take a limit as x approaches plus or minus infinity, it doesn't matter. The bottom is going to go to 0, or it's going to get huge infinitely faster than the top. And so when the bottom of the fraction gets big and the bottom of the fraction doesn't, right? Bottom of the fraction gets infinitely bigger, the fraction goes to 0. And so we know that if we were to take the limit then, the limit of y as x approaches plus or minus infinity is 0. So we can indicate that on our table. The limit as we approach negative infinity is 0. The limit as we approach positive infinity is 0. So we can see we got a horizontal asymptote there, right? That just shows up on the table. Okay? All right, so we got a lot of stuff without really doing any calculus. Is there anything else that we could possibly put in our chart? I mean, we haven't done this yet, but there is. What about a 0 of the function? Where is y equal to 0? At 3. You know, just if we want to have a point, we could plug in at x equals 3, y equals 0. So we get a 0 to anchor our function base a little bit, right? Okay, now we do have to do a little calculus stuff. Okay, so this is going to be a quotient rule issue, right? So we want to use, we don't want to do this, right? We don't want it in factored form. We just want it written as a rational function, right? That's going to be a mess. We're going to have a product rule on the bottom as part of our quotient rule. Just go there. So what's y prime then by the quotient rule?
Low D high.
Low D high.
So it's x squared minus x minus low D.
Okay, times 1. Okay, minus,
High D low.
okay, what's D low? By the way, Kirk, what's D low?
Oh, 2x minus 1.
Okay. Okay, all divided by, what goes in the bottom quotient rule? Bottom squared, right? Okay, and so what do we got? If we simplify that, I'm gonna get x squared minus x minus 30, and if I multiply this out, what am I gonna get? Minus 2x squared minus x minus 6x, so minus 7x plus 3, and if I distribute the negative, what am I getting here? Negative x squared minus x plus 7x plus 6x, negative 30 minus 3. Okay. And so, I just made this one up. Probably shouldn't have made one up. It's not looking at, it's gonna be a little ugly. So there's our derivative. Let's assume that all we're trying to find are relative extremes. Because it's gonna be kind of nasty to take a second derivative. And the ones you'll get in the assignment are much nicer. They don't have cross terms and things in here, so they differentiate much more easily. So we could do a second derivative more easily if it was. This one's gonna be kind of a pain to do a second derivative. But let's at least find all the relative extreme and use the table to do that, okay? So where do we find our critical numbers then? What are critical numbers exist? Where it's undefined. Okay, but where the derivative is undefined, that's gonna be at the same, I can still factor the bottom, it's gonna be at the same place as where the function is undefined, right? So are those critical numbers? No, because they're not in the domain, right? So we only want to find, so the only place we're going to get it is where the top equals 0, if there is a place where the top is 0. So we'll set the top equal to 0 and find out. Y prime equals 0 when the top equals 0. Okay, so let's multiply through by -1. Make that a little easier. What can you tell me about that?
It's gonna have a negative discriminant.
Yeah, can you ever see that? So if we think about that, that's clearly not gonna factor, right?
There's 36
so-
times 4 and minus 4 times 33.
Right, so if it doesn't factor, then we're gonna use the quadratic formula. We always start with the discriminant, start with the part under the radical, and just see what sign you're gonna get. So the discriminant, b squared minus 4ac is gonna give you 36 minus 4 times 1 times 33, which is obviously a negative number, right? So we don't have any zeros of the derivative. So are there any critical numbers?
No.
Are there any extrema? No. No, there aren't. And if we were to finish up our table, there's not a lot to see. The only thing we'd probably want to do is just know what is the sign of it never changes. Well, actually, that's not true. That's not true. Forgot about the asymptotes. If we've got these vertical asymptotes here, we just need to know what's the sign of the derivative in each of those regions. Because the reason I wanted to do one of these is I wanted to talk to you about what these vertical asymptotes mean. It's like it breaks up this universe into different, like they're just completely different places. The vertical asymptotes just wall off each region from the others. And so all I'd have to do, being as there are no critical numbers, and so there are going to be no peaks and valleys, but I need to know, is the function increasing or decreasing on each of these intervals? And once I know that, it's going to be pretty easy to sketch. Okay, so we'll pick a test point on each interval. How about this one right here at 3, for example? If we evaluate the derivative at 3, what do we get? So let's see, if I plug, I just want to know what the sign of the derivative is at 3. Top is going to give me negative, isn't it? Do you agree? Top's negative. So f prime of 3 equals negative over, what's the bottom going to be for sure? Positive, because it's being squared. So it's negative. And we know on this interval, we get a negative first derivative. How about if we pick something like -10? What's the sign of the top going to be? We're going to get negative 100. It's -6. It's going to be negative, isn't it, still? Right? So I'm still going to get negative over positive. And what if I pick something like positive? Let's make it an obvious number. Let's pick 100. You're just going to get a really big negative number on the top again. So it's always going to be negative. So what's this thing look like then? If I've got vertical asymptotes at -5 and 6, the horizontal asymptote is at y equals 0. We can sketch this thing. So we know we got a horizontal well, we've got asymptotes at -5, +6. It goes through the point 3, 0, so it's going through the point right there. The second derivative is always negative, so what's this thing gonna do? It's gotta stick to these asymptotes. So can you kind of see what the behavior has to sort of be like? It has to go through that point. It can't flip over, so it's gotta be coming down from infinity, because it can't ever turn, there can't be a peak. So it's just gotta do something like that, doesn't it? Right? Get the idea? Is that exactly right? No. I mean, if we really wanted to pin it down, we probably want to go find inflection points. But if we're not really looking for them specifically, this gives us a pretty good idea. What's it have to do over here? If it's going to be, it has to be asymptotic on y = 0, but it has to use that asymptote. What do you think? You want to take a stab at that? How can I stick to the asymptote y = 0? Right, so it's got to stick to that. Here's the asymptote horizontally. Here's the asymptote horizontally. There's the vertical asymptote, but it's got to be decreasing. Yeah. So it's got to go like that, right? And over here, it's decreasing, and it's got to use both asymptotes. Yeah. You see that? Yeah. So, taking those limits is kind of useful, right? So I want to go through one more of these, but why don't I not do it today? I'm assuming you guys would like to work a little bit, get some questions answered. Okay. So we'll go through one more rational one tomorrow. You can be working on the 3.6. 2 assignments are up. Might do, they're really short. The first one is like 5 minutes. We went through a lot of the problems yesterday. Second one has 1, 2, 3, 4, 5, 6, 7, 8 problems. Probably do one other one with like 4 or 5. Okay, so you got stuff to work on.